So I'm going to talk about a combination of things with the sort of charge of talking about observations that we might need in the future and sort of ongoing plans for those things. I sort of took things that I'm more comfortable with. So most of my work focuses on ice shelf dynamics and fracture mechanics. So I'm going to talk a little bit about observing those and then move on to a new mooring instrument that we're building at Woods Hole. So sort of split talk, but hopefully related. So we've seen this before. Helen showed this. This is from her science paper that came out in January looking at Antarctica in 2025, showing again that a lot of the uncertainty in future mass loss from Antarctica stems from our sort of current state of understanding of the physical processes at the dynamic margins or edges of the ice sheet. And so what I'm going to focus on today is rifts, which are right here, and then basal melting, which again is right here. This is also from that same paper, also from Jeremy Bass's review paper last year. So looking first at iceberg calving as a mass loss mechanism, and then at basal melt. So first, for those of you who aren't entrenched in this, rifts in Antarctic ice shelves are fractures that often serve as the eventual calving boundaries for icebergs. This is a nice example of an iceberg that broke off in 2019 from the Amory ice shelf from a rift that first Helen had looked at in the early 2000s, and then during my PhD I spent a bunch of time staring at it, and then about 10 years after that it finally decided to do something interesting. But nicely we were able to monitor that. But so we spend a lot of time looking at how these propagate to figure out how we can predict calving of icebergs. So I like to think of this as sort of stages of remote sensing understanding. This sort of follows from Helen's talk, the eras of altimetry earlier in the week. What we first knew about rifts was this is the Filchner ice shelf over here, pictured very early on in the 80s, and you can see this big rift that was called the chasm at the time. And this quote from a paper in 1988 basically saying that, wow, can you believe it? We know more about the ice sheet now than we did before when we were just walking around on it. Now we have pictures to get sort of a context for what all these big features are. So, you know, we sort of went from field-based, walking around on the ice shelves and figuring out there's these big features, being able to see those through imagery, eventually having enough imagery to string together time series of propagation. And then moving forward into the mid-2000s, Eric Leroy and his colleagues started using synthetic aperture radar to look at deformation associated with propagating rift tips on the what is that, the Ronny ice shelf. And then eventually also in the mid-2000s when ISAT, the original ISAT was flying, Helen and her colleagues showed that altimetry actually did really well in showing us what the sort of vertical morphology looked like around rifts. This example is from the Ross ice shelf. So that leads into a little later in the 2010s, during my PhD, we started looking again at sort of going back in time, using imagery to look at the propagation of rifts around Antarctica, not just focusing on a single ice shelf, but trying to figure out what rifts act like in a variety of ice shelves. What we did was use MISR and MODIS imagery, which has a 250-meter resolution or so, and we mapped 72 rifts over a decade, and we sort of came up with this categorization scheme that we could filter sort of levels of activity into. So dormant is pretty obvious over that 10-year time frame. These rifts didn't do anything. They just sort of were big rifts, but they didn't move. Sudden bursts were these, obviously sudden bursts of activity, intermittently active, and then continuously active were ones that were, over that decade, continuously propagating. We didn't see that many of those at the time. Update is that sort of since then up till now, we've about doubled the number of rifts that we've looked at and expanded the number of ice shelves that those cover. But now use Landsat imagery, so moving into better resolution imagery to look at smaller scale propagation events, and about doubled the time scale as well, so over 2 decades of propagation. And you can see that there's a few more that we can see that are actually active over the 2-decade time scale than there were over just a decade. And so now we're starting to think, now that we have ISAT-2 in the last now 7 years, I guess, how can we redefine these categories of rift behaviors to actually accommodate or actually account for the not only the sort of planform propagation that we can see in imagery, but how can we take into account the morphology that comes along with that activity as well? So this is sort of a complicated, messy plot, but all that matters here is that these 3 blue outlines are 3 rifts in a row right on the Ross Ice Shelf. These are approximately 100 kilometers wide in this direction and a few kilometers in the along flow direction. And we're going to look at this green profile line right here. And this is ISAT-2 flying over those 3 rifts. So this is this back one right here, middle one, and then this front wide one is right here and a few intermediaries here. So if we look closer at those profiles, you can see, so this back rift called RS3 is an active rift. It's been propagating since about 2002, and it's widening every year. And you can see that, hopefully you can see, that there's this funny bump that happens at each side of the rift. You get this uplifted flanks and this sort of flexure right at the side. This old rift, which has been around for hundreds of years, maybe thousands, you have this really rounded off, eroded edges, and you don't see that flip at the sides. So we can tell, sort of Helen alluded to this on Monday, you have this sort of signature of activity just by looking at topography and morphology of rifts, not just looking at their lateral propagation. And this is just an example from actually original ISAT, from purple to red is the newest, and so you can see that rift tip just sort of propagating through that orbit track, which is pretty cool. The other thing that we noticed about active rifts and dormant rifts is that you get this offset between the landward side of a rift and the seaward side. So if you think about if you sort of look at this, I should start with this then. These are those same 3 rifts. And no matter if you're sort of rounded off in the old relic rift or the new propagating rift, you have this offset of about 1 to 2 meters, which doesn't seem to be that big a deal, but it can't be explained by the difference in thickness on either side of the rift. And so the question is, why do you have this? Every rift that we've looked at has this offset between the landward and seaward sides of that rift. And what we found is, so this is a little convoluted, but if you take the height of the rift flank on the landward or of the seaward side and subtract the height on the landward side, if it's positive, you are higher on the seaward side. If it's negative, you're higher on the landward side. Might be obvious. But what we found is that it varies across ice shelves, but within the same ice shelf, it's consistent. So if one rift in the Ross Ice Shelf, for example, those signs are negative, they're all negative. And so the question is why do you have this consistent offset between sides of the rift that can't be explained by thickness variation across the rift? What we're able to do, based on both that rift flank morphology that we see in active rifts and this sort of offset of 1 to 2 meters, is figure out that you can sort of model these things as terrestrial fault zones with a dip angle between 1 and 10 degrees, pretty shallow, and you get that same 1 or 2 meter offset. And so hopefully, eventually we'll be able to use things like this to better model rifts in ice sheet models or models of ice shelves. And then we could sort of develop this idea of, over time, using both imagery and altimetry, you can figure out sort of where in a rift life cycle you are based on its topography at the top. So again, as it's forming and in the middle of its life, it has that uplifted flank at the edges, and then it rounds off. So you can sort of figure out if you are, where in the life cycle you are, and then also how active it is or is not. To tie this back to technology and what we're talking about in this session, it's important to note just within the last 20 years or so that altimetry over terrestrial fault systems and high resolution altimetry in particular, observations have revolutionized our understanding of how those work. And so we're sort of following that track in glaciology, figuring out how to use morphology of fracture zones like this to understand the dynamics that are happening. And so if we can capture topography and deformation morphology along rifts just as well as they do now in terrestrial fracture zones, we can improve models of rift propagation and calving dynamics in ice sheet models, hopefully understand the rift propagation state and rift type, and their formation mechanics, which are very sort of clouded at this point. We can figure out, this is some work that Menghan Huang is doing at UMD, looking at pairing these types of remote observations with seismic profiles to figure out where ruptures happen, looking at how fracture-induced alteration and redistribution of stress affects ice shelf stability, and then the influence of intra-rift melange that you have sort of falling into the rift, which is, and how that stabilizes or destabilizes ice shelves, which is Chance Roberts at UCSD working with Helen is working on that. So that comes back to EDGE, which is the mission that Helen was talking about on Monday. And this is just a sample. So that original image that I showed of that iceberg that broke off from Amory Ice Shelf in 2019, after we had all stared at it for a long time expecting it to do something and it didn't. This is that rift that eventually capped that iceberg in Amory Ice Shelf. The blue lines are ISAT-2, which at the time was higher resolution than we ever had before, and it was really awesome to be able to see those profiles right before the iceberg broke off. We were able to map sort of the front change as that happened. Helen showed a much nicer image of that earlier this week, that we could see sort of in high resolution how that front changed as the iceberg broke away. But just to show you what an improvement EDGE is going to be in cases like this, where we can look at the morphology along the rift in much higher definition. So these profiles were from ISAT-2, and were roughly 4 to 5 kilometers apart over a year. There's a lot of dots here, but essentially look all the way on the right here. This spacing is about 0.3 kilometers. Over the same time period, we would get this many samples along that same rift. Instead of 4 to 5 kilometers, you'd get a sampling every third of a kilometer, which would be pretty awesome. Okay, so moving on to the next part, next observational system. So this is much more in process, not so many science results to say for now, but looking now at the basal melting part of mass loss. Thankfully, Yoshi and Eric and other folks have already talked about the oceanographic side of this. I'm not an oceanographer, so it's very uncomfortable for me to try to be an expert at that in front of you all. So they've done a much better job than I can. But the question that Yoshi posed yesterday when he was talking about his work is very much what we're asking as well. So how does warm water reach ice shelf cavities? What does cavity circulation look like? And what controls the basal melt rate? So we've already seen this figure nicely, but so looking at that CDW spillover onto the continental shelf, getting up underneath ice shelves is what we're sort of aiming to measure. Of course, the ice shelf ocean boundary is not this sort of perfect flat thing like it shows here. Well, I guess there's some cracks, but you have a lot of complexity there, a lot of corrugation and crevasses, and things that sort of alter the circulation at the right at the ice ocean boundary. You have heterogeneity in basal melt distribution, and an inhomogeneous meltwater outflow and cavity circulation, which doesn't really show well on here, but a lot of different things going on in different places. It's not homogeneous at all. So Helen also showed this. This is a map from Sushil's paper in 2020 that shows this is sort of what we take as the measurement of ice shelf basal melt rates from satellite altimetry. But few observations have been directly collected in ice shelf cavities to date. I'll go through a few of them, certainly not comprehensive. But, and then also, obviously, as Eric and Yoshi and others have sort of pointed to, there's a lot of sort of modeling work that has gone into understanding that inflow of CDW and how it gets up underneath the ice shelves and into the cavities and how that impacts basal melt rate. So Craig is going to talk more about this more expertly than I can, but just to go through some existing technologies that we use now. So sea gliders have been used. These went underneath dots in ice shelf a few years ago and lasted for quite some time. You can see the profiles here on the right and measured ocean conditions underneath that for a few months. There's also big AUVs. These are sort of have to be deployed from large ships, obviously. So there's like the Hugin that was used in the Thwaites project, AutoSub Long Range, and AutoSub 3 before that. And these sort of are big, logistically challenging things to carry out. There's also some borehole and through ice AUVs. Obviously, I think most people know about IceFin. There's also Artemis down here, which is a big sort of flat-looking thing, and then Skinny, which is also deployed through a borehole. And then there's just borehole moorings or CTDs that you can send down through the ice that can get down to the seafloor in some cases. Some cases are just anchored to the bottom of the ice. So the sort of data that comes out of that, we've already seen this a few times as well, but this is from near Pine Island Glacier. You get some data underneath the ice shelf, a lot more transects outside of the ice shelf, but a little data underneath. It spent AutoSub 3 spent about 94 hours underneath Pig in 2009, and another 94 hours in 2014, collecting this really useful information, but of course limited in time and in space. I just really like this plot that they got into a paper, so I like to put it wherever I can. It's sort of a dream to get like drawings like that into a paper. So this, the Hugin, or Ron, I think, went underneath the Dotson ice shelf as well, collecting oceanographic conditions sort of within 80 meters of the ice-ocean interface during 4 missions in 2022. And then the IceFin went near the Thwaites grounding line and made those important observations that you get a lot of melting along these sort of steep topographic slopes at the bottom of the ice shelf. But the long story short here is that there's not a lot of data. There's some really great data, but not a lot, particularly in time or in space. So when I first got to Hui, my question to some of the engineers in my department was, can we just take one of the moorings that we have here and stick it under an ice shelf? And they said absolutely not, several times in many ways. But we eventually sort of said, okay, what are the requirements that we would need and things like that. So I asked, eventually, the requirements essentially were to have some long-term or multi-season continuous measurements underneath an ice shelf, direct measurement at the ice-water interface, try to avoid long-term ship presence or a big logistical need, and no borehole drilling. So that's sort of the setup for what comes next. Hui, for folks that aren't familiar, is the home of the Ocean Observatories Initiative, so they have a lot of experience building these big open ocean buoys that are anchored to the seafloor and do a lot of measurements in the full water column. We have a lot of vehicles. The one that we're using in particular is the Nereid Under Ice ROV, which is this big, it's sort of the size of a smart car. It's connected via a tether, but it's mostly autonomous, built to go underneath ice. It's been on several Arctic expeditions. First, we were going to use NUI just to deliver an OOI buoy underneath an ice shelf, and that was the one that was like soundly rejected because the buoys are way too heavy. And so eventually, and I should mention this is funded right now by the Keck Foundation, we came to this conclusion that the best design would be to have a self-navigating mooring drive itself underneath an ice shelf and deploy for long-term deployment. So I'll go into a little bit of detail on what that looks like for now. We're about a year into this project, and we have another year ahead. So we're mostly at the design phase now. We have our mission design review next week. But this is what it looks like. So this is a repurposed NUI vehicle, Nereid Under Ice vehicle. It's still about the size of a smart car. This is essentially going to bring itself underneath an ice shelf and deploy a mooring riser cable anchored to the seafloor, and then have this little variable buoy. Oh my God, variable buoyancy. Oh my God, I have so much trouble today. Variable buoyancy buoy, VBB. We'll just go with that. That's going to sort of fill in that last 100 meters to the ice-ocean interface because we're not quite sure where that'll be at all times. And so it'll be a little more flexible than just this big sort of mooring riser here. It's about 3,200 kilograms. It's 700 meters tall. And it's got a 20-kilometer, I should have mentioned, seafloor fiber optic cable. and battery operating for about 2 years at least. So just a little more information on the deployment. So it's going to swim in underneath. It can go, I should have said this before, it can go up to 10 kilometers underneath an ice shelf and deploy there, put its anchor on the bottom, and then rise up to 100 meters below the ice, and then deploy the VBB here that it can track however the ice bottom is changing. The payload architecture for now, this has been the majority of the work so far, is fitting all of the payload desired payloads, I guess, on the science side with the power requirements. So we're going to have a science payload made up of ADCPs and hydrophones and a CTD on the NUI itself, and then a bunch of instruments along the riser. And then, again, CTDs and an altimeter, at least, to look at the bottom of the ice on the VBB. This is what the VBB looks like. I was imagining like a sort of a small buoy-looking thing, but it's actually the size of a person. So this is the just early design for what the piece is that's going to be following the currents and going along the ice-ocean interface. So it'll actually touch the interface and then come back down and go back up, and it'll do that 8 times a day. Oops. So this is sort of the dimensions of the whole system. It's about 7 feet wide and 17 feet long. And the riser pack, so this has been a significant design challenge, is making sure that this can deploy without tangling the instruments in that. That'll be, I guess, a sort of fear factor test when you actually have to do it. But this, and then this drum below will carry the 20-kilometer fiber optic cable. And again, the VBB will be bouncing back and forth between the MDM and the bottom of the ice to get that sort of last 100 meters of the ice-ocean interface. You might be asking how we're going to get anything back from this. So that's the reason that we have a fiber optic cable for the seafloor. It's going to connect to a second mooring that's outside of the cavity that's going to be collecting the data. It will also have instruments on its own riser here to measure both outside and inside the cavity. And this is based on a design called Ultramore that we designed in the early 2000s that will have data capsules sitting here at the top. It also won't have a surface expression to avoid getting crushed by icebergs, but it'll eventually send these data capsules up periodically that can connect via satellite. Okay, I think, yeah, the main point here is that so we're in the middle of this design phase, obviously, but I guess, big overarching question that you might have, and certainly our reviewers did, is, what's the value of just having this one data point? You have continuous measurements at one point, but what can you say? Did you put it in the right place? Are you getting the outflow, or are you just sitting in the middle of sort of uninteresting part of the ice shelf? And the sort of drive-home message here is that it's meant to be very complementary with existing technologies that I talked about before, like AUVs, ROVs, gliders, and things like that. So, in the sort of mission sense, this can provide a temporal variability that those can't collect, but then the spatial aspect can be filled in by hopefully existing and developing technologies. So this is just a map showing, the pie in the sky plan is that we could deploy these things wherever we're interested in, underneath ice shelves in Antarctica. And this map shows anything that's colored here is a place that our design requirements, so up to 1,500 meter seafloor depth and up to 500 meters draft of an ice shelf, this can deploy underneath. And so you'll notice that some parts of like Amory ice shelf are grayed out here because we can't get all the way underneath that sort of deep keel depth. But you can certainly get towards the front, which we're limited to the first 10 kilometers anyway. And so almost every ice shelf around Antarctica has a deployable site or a candidate site that we could go to. I think this is the last slide. I think, so our test, or our full systems test, is at the Mid-Atlantic Bight at the shelf break next July, a year from now. We're going to be deploying the full system. Obviously, there's no ice, and so there's a little bit less risk because you can just pick it up out of the water. And it'll be a little shorter, but we'll be deploying the whole thing for a week next year. And the takeaways, I guess I'll just get to that. from both the rift part and the under ice part. Improvements to process scale observational capabilities. I'm sure everybody knows this already. Both time and space is necessary to advance our understanding of these processes that contribute to mass loss from Antarctica. Complementary technologies are very essential. Nothing can do it all. Even, EDGE will be sort of modified by imagery and SAR and things like that. This will improve everybody's ability to sort of parameterize these complex processes and improve models. And much like EDGE is meant to be a community LiDAR, this hopefully, as it comes along and we get follow-on funding and things like that, this will become sort of a community tool that we can all use and modify. Because, as I said, certainly not an oceanographer, and so people with better payload ideas or deployment ideas certainly welcome. So that's it.
Thank you.
Great.
Questions?
Hi, Catherine. A great talk. Thanks. I'm Becca Jackson. Let's see. I have so many questions. This is so cool. Maybe I'll start with the fiber optic cable for NUI. My understanding is usually it's very thin and kind of fragile. Yep. When you deploy it in this, and so I think the advantage there is maybe it doesn't have much resistance, so you can do all sorts of surveying. When you're doing it in this application as a mooring instead, is it going to be a little bit more protected, or do you have either a contingency plan if it's not as protected, or are you adding more covering to the fiber optic cable?
Yeah, so I skipped over that, but yeah, so Becca's right. The tether that goes with NUI is thinner than a human hair, so it's very thin. So it's going to be armored to lay on the seafloor, but we're also, I should have mentioned, going to have backup acoustic communications as well, just in case that fails.
Hi, yeah, awesome. I also had just a clarification question on the setup. In all of the cartoons, the NUI is still there. Does it stay there the whole time? I was just a little confused about that.
Yes, so the body of NUI will hold a few payload items too. So it'll hold a CTD and an ADCP and a hydrophone, and it'll stay it'll essentially serve the place of a buoy on a normal mooring.
Oh, right. So
it'll
it's part of the longer term.
So it'll stay there.
Right.
Forever.
Are these something that was told you have a bunch of these?
No.
Oh, okay.
No. Honestly, so to keep our costs down in this phase, we're deconstructing the existing NUI to put it back together at some point. But the plan would be to then sort of multiply the NUIs that we can then leave underneath.
Yeah. Okay, cool. That helps. Thanks.
Yeah.
This is really cool. Can you talk a bit more about the VBB, and in particular, is the idea to get really close to the ice, and where in the multi-layered boundary layer structure do you hope to get? And I guess the point of variable buoyancy is that if there's changes in melt and the stratification, you can adjust to stick maybe within a certain distance from the ice edge, or what's the idea there?
Yeah, so most of that, the idea there was we didn't want to presuppose any specific height that we wanted to be at, just in case, assumingly once we pick a target ice shelf, we would sort of have an idea of how deep the draft is, but didn't want the mooring or the NUI, basically mooring top, to get hit by anything or be scraping along anything. And so the idea behind the VBB was to have something that could depart from the main instrument station and sort of take profiles there. And the overall idea is to have it be able to touch the ice and then come back eight-ish times a day. Particularly if we can so we'll have an altimeter on it, and hopefully if we can get up into crevasses and things like that and let it stray up there and then come back over time. So hopefully it'll pass through, that sort of thin boundary layer right at the ice-ocean interface.
Awesome, thanks.
Alice?
This is really cool technology. I know almost nothing about this, so I'm sorry if this is an ignorant question. But you were saying, so the NUI will just stay there. is the anticipation that you guys would recover it at some point, like before the batteries die? Or if not, how long do you expect that it would be deployed there before the batteries die?
So the initial sort of design requirement is for the batteries to last 2 years before it turns off, with some margin. So hopefully if it lasts more than that, that'd be great. But yeah, I guess in a less cool way, the plan right now is to leave it there, which is not awesome. But one of the motivations to base it on NUI specifically is to have this sort of payload package that once we can get, if people are interested in less endurance or some shorter period thing, we could eventually make it so that, okay, pick it up and turn it around. So we do have the ability to recoil everything and swim back out, but yeah.
Thank you, Catherine. This is exceptionally cool. I noticed on your diagram of the mooring, there was biogeochemical sensors. What are the conversations y'all are having around, what are the features of interest or, variables of interest there?
That is a good question. So that one is not decided upon yet, mostly because we have to, so this is the value of coming to places like this, meetings like this, and I should have said thank you for inviting me. But to get sort of other inputs, because right now it's just me, who's a glaciologist, and Gordon Zhang, who's a ocean modeler, but we don't have a giant team. It's mostly engineers at this point, very valuable engineers. But yeah, to try to come and get like the most valuable information we can. Of course, we have really sort of constrained power requirements and data requirements, but we just sort of had that as a placeholder for things people are interested in.
That's really cool. Thank you.
Hey, thank you. I had a question about the earlier part of the talk and the rifts that you were saying, which were at different heights. And so you're saying that the height offset is the same along any individual rift, but it varies between rifts. Do you guys have an understanding of that? Does that give you some sense of what the residual stress is before the fracture forms?
Yeah, so hopefully, that's the, I guess, intent eventually. So it's both consistent along one rift, and every rift within the same ice shelf has the same offset. So it's, we were thinking of it as a way of, it must suggest something about how rifts in that particular ice shelf form and how the stress is distributed between different ice shelves, but we haven't done like the full figuring out how that informs on stress balance, but it's the intent.
Patrick?
Hi, yeah, this is really cool work. A question on the SAMs. So the atmosphere community has developed this concept of targeted observations. Basically, they're trying to predict or simulate what placement of an observing system has the maximum impact on the quantity that you want to observe. Is that something that you're pursuing? Yes.
So so Gordon Zhang, who's the co-PI on the project with me, he spends a lot of time modeling ice shelf cavity circulation, and so eventually, once we get to that point, I think, hopefully with other people's inputs as well, we can figure out sort of, once we target an ice shelf, figure out where exactly we should put that. I'm sure eventually we'll be off anyway, but yeah, figuring out. We can also use sort of surface information too, looking at like basal melt channels or things like that we want to target.
Great, thanks.
This is incredibly cool. It's so cool to see this technology coming along, and I think it'll be amazing for its science returns. Just wanted to follow up on a couple of the previous questions about, so the vehicle is staying there, and in principle, you say in the future it could pick itself back up and exit. Does that mean that it could also potentially pick itself up and reposition itself during the same deployment if you wanted to sort of get a little bit of spatial information?
Yeah, I suppose it could. I think the limit right now is just that 20-kilometer fiber optic cable.
Got it.
But if people are, I guess, if the engineers or whoever is making decisions at that point are comfortable just using the acoustic communications, then we can sort of splice or split the tether and move eventually. Yeah.
Just curiosity, you say 20 kilometers, the cable. Is there a limiting factor in terms of like the communication, or is it just you can make a longer cable in theory?
Yeah, we could make a longer cable in theory. It's mostly confined right now by the space available on the spool to unspool as it goes along. But
And a related question, sending power, is that something completely crazy? Or from moving outside the ice?
Yeah, it would be cool. I kept pushing for that because then we could operate forever. Really cool. So based on NUI anyway, NUI's cable fiber optic tether is only communications, not power. And so since we're basing it on NUI for now, we're limited to not wired power. But yeah.
I was just going to say in terms of the biology sensor on there that at least in the Ross Sea, the marine protected area, it extends all the way under the ice shelf. That's technically the limits of it. Who knows if there'll be other marine protected areas, but in that sense, having information about the biology under there could be really valuable for encouraging protection.
Yes, awesome. Great.
Hi, Catherine. I'll say what everyone else said. Very cool. Just coming back again, is, one of the things that I think many of us have really wanted was in situ observations of the boundary layer underneath the ice shelf. And I know one of the big challenges IceFin has had, for example, is that existing CTD technology is not designed to non-intrusively measure within order centimeters of a hard boundary, right, or a hard surface. And so there was a whole PhD of someone redesigning CTDs to be much smaller. If with what you said before in answer to one of the other questions, how do you imagine, would it only be if there's a rift where the VBB is traveling through the boundary layer, or how would you be able to take a measurement from there?
Yeah, I think so. That's a good point. So we've had a lot of conversations with RBR and other folks who have pointed that out extensively. Yeah, so I think what we were trying to capitalize or leverage, I guess, is that it'll be in that same spot over a long time, and 2 years, and hopefully in that time enough bottom topography will change that you sort of get to pass through something that is like a plane boundary, but not exactly. But you get some sampling across a sort of, I guess, imagined boundary that won't necessarily be we won't get that last whatever in totality, but you can get some sort of average about what's happening near the ice versus off from the ice.
Could you imagine in the future, I know this is clearly not in the current design, but deploying something that is buoyant that just sits on the bottom of the ice and then could communicate back with the main vehicle basically, and would just kind of ride along that way? It would just potentially be small enough that it could just kind of sit in there and kind of measure things continuously over time.
Yeah, and so one of the discussions we've had, which obviously isn't in this now, but using this more as a sort of delivery vehicle for other things. And so if we can use it, I kept using the analog of if anyone's seen Twister, original Twister, not the new one, but the Dorothy thing, and they sent all those sort of things up, not to litter the ocean, but sort of bring in a capsule of things and that could float up and actually attach to the bottom of the ice. Yeah. Not having to use borehole drilling, which was, to be honest, my initial sort of way to get past the sort of ice fin, well, not even that ice fin's limited, but sort of get past that sort of thing where you're limited by a tether when you go through a borehole. That was my initial idea, is can we not use a borehole? And so using this vehicle to do other things that would not require a borehole would be sort of the ultimate.
I know that the ice fin, they've thought about docking before, yes. And there's been some tech development in that direction, but yeah, it's a challenge. Very cool, thanks.
All right, that's the end of our question session. So if you can catch up, Catherine, if you have any other questions afterwards during the coffee, but let's thank her again.